Namaskar. So let's see in this lecture about how to connect, if you are connecting different cells in series or parallel combination, then how you can find the EMF of the combined network, and what would be the internal resistance and EMFs in the equivalent EMF for this cases. So let's see. So before that, let me tell you that how to represent a cell in a circuit. So in the previous lecture, we had discussed that load resistance and electrolyte cell. So that can be represented like this, where you have two perpendicular lines separated by a small area, and one is bigger and one is smaller. The bigger one represents the plus and the positive electrode, and the smaller one negatives. And this is how the current flows from the positive to negative terminal. So this is a representation of cell and connected to a load, right? So now coming back to the point that if the cells are connected in series, so series means if the one of the end of the two cells are connected, then they are called connected in series. So for example, let's say we have two cells, and for the time being, no, you can just connect the two cells, once negative electrodes connect with the other one positive. You can also connect the this negative to the other negative, and then we'll see that what will be the changes in that case. But see the main point with this first. So let's say this is your point A, and they are connected at point B here, and this is some point C, right? And let's say this is your cell 1, which have electromagnetic force epsilon 1 and internal resistance R1, and here epsilon 2 R2, right? And as I said, the current flows from positive to negative, so it will be the direction of the current would be this, right? Okay. Now we want to find the equivalent between A and C. So let's say this is your A and C, and here we want to have a equivalent cell, right? So we want to find out what will be the epsilon, the EMF equivalent value, and R equivalent value if we have the combination of the two, right? So between A and C, we want the equivalent cell and the equivalent internal resistance. This is our aim to find out. Okay, so to find it, first let's see if these both are current are flowing in it. So in that case, what we can write, we can write the potential difference between A and B. Potential difference, I am writing with P dot D, the small acronym for this. Potential difference between A and B, it can be given as what? It can be let's say VAB, right? So this can be potential at A minus potential at B, and just we have seen that for this kind of a structure in our previous lecture, it can be written as epsilon of minus if the current is flowing I, and both current same current will flow in through both, so it will be I internal resistance R1. Similarly, the potential difference between this and this, so BC, it can, let's say it is BC, so it can be potential B minus potential C, and this you can write as epsilon 2 minus I R2, right? So we have a VAB, we have a VBC, right? So these are the two equations. Now to find out the equivalent EMF, so we want between A and C, so let's find out that what would be the potential between A and C. So it can have potential A minus potential C. Okay, so we can just add something and subtract something because it is a point position dependent, not the path dependent. So you can write let's say plus B, right? And then you have a minus here. Let's say here you can minus B, and then you add plus B, right? So it will not be mattering, and then you have minus VC. Okay, so you just slightly arrange, and then you can write these two as VAB plus VBC. Okay, the potential between these two. So you add up the both, and then you can write VAC equal to, so you can write VAC equal to epsilon 1 minus IR1 plus epsilon 2 minus IR2, right? So you just slightly arrange, and you can have epsilon 1 plus epsilon 2 minus IR1 plus R2, right? So as I said that now between A and C, if you want to have a equivalent epsilon, and R equivalent. So you can just for this you can write an equation, and that can be potential difference between AC is equal to epsilon equivalent minus I R equivalent if I current is flowing through it, right? So if you compare this equation and this equation, then you will get that epsilon equivalent is equal to epsilon 1 plus epsilon 2, that EMF 1 plus EMF 2 you can say here, and R equivalent would be R1 plus R2. So you can see that if the two cells are connected in a series like this, and with epsilon 1, epsilon 2, R1 and R2, and the current flowing like this here, then you have you can add up the individual EMFs of the cells to find the equivalent, and for internal resistance you can add up to get the equivalent resistance, right? And similarly you can have n cells like this, and you can find for n cells, so you can extend it to so many cells. Now one important point to notice here, that here it is current is these cells are connected, this positive to negative to positive. So you can also have a series connection where you have this flowing like this, where it is connected to the negative in the other cell, right? So it can have a combination. So in such case, once you have epsilon 1, so in this case if you are reversing it, then this would have become minus epsilon 2 becomes minus epsilon 2, because it is the current is on opposite direction. So here the current flow like this, and here it is opposite direction. So you will have the EMF represented this epsilon 2 tends to minus epsilon 2 in such cases. So in this case you can have your epsilon equivalent is equal to epsilon 1 minus epsilon 2, because this plus epsilon 2 EMF 2 is replaced with the minus epsilon 2, because here the polarity is reversed. Similarly, but it will not impact your equivalent resistance, it will remain the same, it will be having 1 and 2. So you just have to remember that how they are connected. So you just if it is connected like this, and the current coming out from the positive and going in the negative, then it is taken as positive. Otherwise, if it is vice versa, then the opposite way, then it would be written as a minus sign. So that thing you should remember when you are solving this kind of problem. So now moving further, and let's have a look if we have the parallel connection of it, then how to solve. So for parallel connection, let's say we have two cells like this and this, okay. It have epsilon 1 EMF 2 EMF 1 internal resistance R1 R2, and in this case the both positive are the two terminals are connected together. The of the two cells is not in a series, it is only one connected to the other, but in this case the both terminals connected to the cells, right? So something like this. So let's say this is your point A and this is your point B, and if you see the current, if the current is flowing through it A, because this is a positive, right? So if I, so here it will be, let's say I1, and here it is I2, and here out circuit again it will be let's say this is some point C, and this is some point A, and let's have this point B and B dash, right? So between B and B dash you will have this I2 current flowing like this. Sorry, this is the direction I2, okay. So but the total current can be given as I1 plus I2, right? And since they are connected in parallel, so let's see if there are potential difference between the two between B dash through this, and this would be same. So you can write V is equal to epsilon 1 minus I1 R1, and through this circuit would be V is equal to epsilon 2 minus I2 R2, right? So if you calculate from here, I1 is going to become epsilon 1 minus V upon R1, and here you will get I2 is equal to epsilon 2 minus V upon R2, right? So if you get the total current, if you want to calculate, so you can have a total current I is equal to I1 plus I2, so you can write as epsilon 1 minus V upon R1 plus epsilon 2 minus V upon R2, right? So you just solve this equation, and then you will get I is equal to epsilon 1 upon R1, epsilon 1 you can take like this, epsilon 1 upon R1 together here, and then minus V upon R1 and minus V upon R2 together, right? So you can write epsilon 1 upon epsilon 2 upon R2 minus V 1 upon R1 plus 1 upon R2, right? So this is the simplified form. Further, as we are talking about between A and C to find the equivalent resistance, so let's say you have a cell which have a equivalent EMF epsilon EQ, and then you have R equivalent for between these A and C, right? So between A and C you can write the equation here as if the potential difference between this is as V as shown above, so it will be V is equal to epsilon equivalent minus I R equivalent. So if you get the I from here, so it can be written as epsilon equivalent minus V upon R equivalent, right? So if you can now simplify this equation and compare with this, so that I can be written as epsilon equivalent upon R equivalent plus minus here V upon R equivalent, right? No problem with that. So if you compare this and this, then you can easily write for the parallel combination that epsilon equivalent upon R equivalent is equal to epsilon 1 upon R1 plus epsilon 2 upon R2, right? Okay, and the other analysis if you got from here is that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2, right? The similar thing you can write for young cells. So one other important point here to note here is that here we have connected this the minus together, right? So you can have a arrangement where you have a plus minus, right? This is also a parallel connection, right? But in this case, no, the current is flowing like this, right? So in this case, the current is going through positive and coming out negative. So it means that the polarity is different. So here, if it is epsilon 2, then here it would be your minus epsilon 2, right? So in this case, this would be plus, and this epsilon 2 will become minus epsilon 2, and your equation will be modified accordingly. So this you should keep in mind and remember when you are solving this kind of equations. So the similar concept you can generalize for the parallel. So you can have 1 upon R equivalent for cells is R1 plus 1 upon R2 plus and so on 1 upon Rn. And for EMFs you can have 1 upon R equivalent ratio is equal to epsilon 1 upon R1 plus epsilon 2 upon 1 upon R2 for epsilon n upon 1 upon Rn. So this is for your parallel connection, and if it is in series, then you have R equivalent is equal to R1 plus R2 plus and so on Rn, and then epsilon equivalent it will be epsilon 1 plus epsilon 2 plus and so on epsilon n, right? This is for series. So this is all about how to get the equivalent EMFs when the cells are connected in series or in parallel, and what would be the equivalent value for them. So this is all about this for the lecture, and next lecture we will discuss about Kirchhoff's law. So see you there. Thank you.